Nice if someone who has worked with him introduce the speaker for today. So Shalini, please, can you go ahead?
Thank you, Rahul. So, hello everyone. Let me introduce Dr. Dibyendu Das. So, I don't think there is a separate introduction is needed here. Like everyone knows, but it's still I want to give a brief introduction. Didi is a senior technologist who is working in AI and compilers at the confluence of AI and compilers, and he is also having a work experience of working in deep learning compilers, and in order to improve the performance of the code, and also he explored the various future technologies like enablement of AI in compilers, and working. He is having an experience of working in MLIR and LLVM for ML frameworks. So and many more. And also Didi was leading a team at AMD which developed the AOCC compiler, which is a very premium compilers, optimizing compilers that achieved the world record for spec benchmark scores. And also currently Didi is leading a team in Intel, and currently he is also working in the working with enablement of deep learning models in compilers. And personally, yeah, I also worked with Dd for the loop distribution and vectorization work at many points of many times in during my research. I got I had a discussion with Dd, and we get very knowledgeable and fruitful feedbacks from Dd in order to improve our work. So, and yeah, I think you can find the other relevant work in the Google Scholar page, and you can see the lot of research work which research papers Dd is having in the different compilers and ML related stuff. So thank you so much, Dd. Here he's here to present the talk on ML driven hardware cost model for MLIR. So I request Dd to please take over.
Okay, thanks a lot, Shalini. Thanks for the nice introduction, and welcome to you all. There are a few familiar faces, obviously, in this group, and Ramakrishna, who was Shalini's advisor, a very old friend and an ex-colleague of mine from my early days at HP. So first of all, am I loud and clear?
Yes.
Yes.
Okay,
Yes.
okay, good. So yeah, so today I'll be talking about some work that we have been doing at Intel over various ML frameworks that we want to enable in our hardware and the software stack. And for that, we needed to look at some of new technologies that probably will be driving some of these new things. So let me first share my screen. Is it visible to all?
Yes.
Yeah, okay, good. So mainly this talk was also delivered last year as part of LLVM Dev Meeting 2022, though I could not attend in person because of travel restrictions, but I was able to deliver it online. And this work was done, or is being still done, with my colleague Sandhya Mannarswamy at Intel. So first of all, I am guessing that most of you are familiar with MLIR, which, as most of you may know, is a new kind of IR representation that got kind of an attention about starting 2 years back. It was officially announced or inaugurated in Brussels Euro LLVM in 2019. And since then, there has been, in the last 4 years, there has been quite a bit of work in this area. And the good thing is for companies or individuals or academic groups or research groups working on machine learning frameworks or even on a plain LLVM or other optimizing compilers, MLIR can be seen as a kind of a representation which people would want to adopt or trying to adopt, because it probably gives more flexibility to the compiler writers to arrange stuff, to lower stuff from a high level description to a lower level description in stages. And these kind of stages are usually referred to or created through various kinds of what we call as the MLIR tags, right? So though I didn't give the word high level in my talk name, but I kind of used it earlier mainly because of the fact that MLIR, as many of you know, has various kinds of representation. It's not a single IR like LLVM. Like LLVM, if I discount the machine IR for the time being, is kind of a single IR, and you can see that IR definition. When you go to the LLVM documentation page, you can see exactly the group of intermediate instructions that are supported and which you can lower to. And this kind of instruction usually has stayed constant for a long period of time, other than the fact that there has been some improvements, additions with respect to, let's say, the vectorization framework and other things. But other than that, that IR remains fairly constant. As opposed to MLIR, where there is no single IR as such. So MLIR is just a family of IRs, and these IRs are called as dialects. And you can choose the level at which you will want to represent your dialect, which is a high level, close to your language. Let's say it's Python or whatever language you are writing, Swift, or a much lower level, let's say even something similar to LLVM. So there's a flexibility that you can develop. It's kind of you develop your own IR, which is the dialect, and then you start lowering between these dialects. And while you lower, you try to do various kinds of optimizations. Now, as you may also know, that MLIR provides certain standard dialects which are part of its repo, like the Linalg or the Linalg dialect, which stands for the linear algebra dialect. Things like affine, which is very similar to our polyhedral affine loops. We have structured control flow. We have edit. We have LLVM dialect. We have SPIRV dialect. So these are all various dialects which are supported by MLIR or LLVM project today. And over and above that, you can build your own dialects and get into the standard dialects through various lowering mechanisms. And the standard dialects provide quite a few optimizations on its own, which obviously is being contributed to by the community. Now, what is the problem that we are trying to solve today? Now, this is something we have been trying to do for the past 1 year. I'm not going to say that it's still very successful yet, because it's a kind of a hard problem. And even yesterday, there was some discussion on Gmail from someone who was trying to figure out a similar solution for just from the LLVM-IR perspective. So what's the problem? The problem is I have given a high-level description of a data flow graph. And what does a data flow graph usually means in ML frameworks? So mostly I'll be talking about inputs to ML frameworks as opposed to normal C, C++, Java kind of programs here, because we mainly work in that area. And that's where our Intel hardware or the Habana specific hardware is being targeted for. So for all of these, if you see when you write your code in Pytorch or TensorFlow or JAX, what you have basically at the end of the day, once that program is parsed, is a data flow graph. And these data flow graphs are nothing else but, let me try to take a pointer. Yeah. So these data flow graphs are nothing else but graphs consisting of nodes and edges. And each of these nodes is an operation. This actually is a high-level operation. We should not confuse this with low-level LLVM-IR or machine IR instructions. If you look at them, these operations by themselves actually are big pieces of code. I'll just give a hint of that later, but we'll not go into how we do the lowering from this high-level graph all the way to the code, but I'll just give a hint later. So what happens is, once you write a program in TensorFlow, JAX, Pytorch, or any of these frameworks, you have this kind of a data flow graph. And this data flow graph mainly encapsulates your model. Now, I'm showing a very simple example, but this can be very big, consisting of hundreds and thousands of nodes. So let's say if you want to look today at how a GPT-2 looks like, and if you look at the Onyx ONNX model for that GPT-2 data flow graph, you will see a big piece of graph consists of maybe 700, 800, 900,000 nodes, which each node having these kind of operations. So these are very high-level operations. These operations work on tensors, what we call as tensors. And tensors are nothing else but high-dimensional matrices. So matrix is a two-dimensional tensor. And then the usual tensor is high-dimensional matrices. For example, for our Habana hardware, we support up to 5-dimensional tensors. But if you have higher order tensors, let's say 6, 7, or 8, we need to collapse some of the dimensions of those tensors so that we fit into 5 dimensions, and then you can execute from there. For example, if you go to GPUs, GPUs are basically, by default in their hardware, or the way CUDA is written, you can support up to 3-dimensional tensors. And then if you have higher, you need to flatten those tensors so that you go into 3 dimensions. So mainly what you have is a data flow graph. And from this data flow graph, we have to finally generate our code, right? And for generating that code, it's finally basically a new kind of a compiler. I'll not say even new. It's mainly a compiler. So at the end of the day, this is just a representation of that data flow graph when we generate the top level MLIR dialect for this. And if you are not familiar how this is represented, how this works, let me just go through that. So if you see this data flow graph, the bcast is nothing else but broadcast operations, and div and mul is obvious to all of you. And then there are some arguments, right? And this is the data flow graph. But this graph, usually if you guys, or some of you guys are familiar with TensorFlow frameworks, TensorFlow, when they did XLA, right, the accelerated linear algebra software, which was kind of integral to their compiler framework. So once you had a TensorFlow graph, the XLA used to really work on this graph. I mean, there was no representation like this. It was not really a program that you were optimizing in the traditional sense of when we do IRs and things like that. But you have this kind of data flow graph, and then you will do various graph level optimizations. You will try to, let's say, you'll try to compress. You see a div by some constant. You try to convert it to a multiply, and you can do a lot of these, what are called as graph rewrite operations, right? And then finally, once you are done with all of these graph rewrites, I will expand this kind of stuff, and finally, go to LLVM or something, and then generate the code. But what people figured out very quickly is doing this kind of graph optimization is, in general ad hoc. And everyone will have their own graph representations. They're then doing their own rewrites. And mainly, you are trying to, at every shop which is trying to do a compiler, you are basically reinventing the wheel. And what people try to figure out is, instead of doing that, let's go to a proper compiler methodology, right? You have an IR and you start using that IR and slowly lower it down through your kind of a compilation optimization chain. And that's where, MLR kind of arose. Though ML in that MLR, some people say is not really machine learning IR, but it is like people call it mid-level, whatever they call it. But let's, for the timing, assume that it's an IR which sits at a much higher level than LLVM. And once again, people who have heard of an open source compiler called Open64, which predates, many of your days of working with compilers, maybe many of you have heard of LLVM and GCC, but not Open64. Open64 was originally the SGI, Silicon Graphics Compiler, which became open source. And this is a very well-known, powerful optimizing compiler, and many companies used to work on it in the 2000s, early 2000s. So similar, they had this IR representations called the top level. It's called world, WHIRL, and it's like a top level world and a bottom level world, and they used to lower between this levels before they actually started generating code and things like that. So here, if you see, that this data flow graph becomes something like what is called as the high level. So I'll still use the word high level MLR, because this MLR is just the first level where we enter our compilation pipeline. Okay, so if you see the data flow graph, you can see this will be converted to a function, and then these are these arguments, right, which are coming into this data flow graph, and these are represented as multidimensional tensors. You can see these are the sizes of your tensor, 640 into 3522 of type F32. And there is some type of BF16 for people who are familiar. This is the new floating point 16-bit. People call it brain float or something like that. Came out of Google, and it's a new kind of a 16-bit floating point representation. Not the IEEE compliant floating point. And then these are the arguments, and then finally at the end it returns another tensor, but then it is of type BF16 instead of type F32. So what you do is, once you see this input, the body of the function is pretty easy to read for people who are familiar with LLVM and various dialects of MLR, that we create. So the first letter is the dialect name. So it's called XPU, because in Intel, we support various kinds of processing units, right? We support CPU, we support GPU, we support FPGA, we support Habana accelerators. So let's say we use the term XPU. It doesn't really exist. I'm just simplifying the dialects. But let's say it's called XPU, and then what we do is, under this dialect, we support this kind of operations like broadcast. And the broadcast takes in an arg1, and this is the input type of the tensor, 640 into 1 into F32. We can see the arg1 is type 641 F32, and it returns another tensor, which is broadcast. So which is basically broadcasting your tensor from this dimension, which is a one element dimension, to a dimension of 3052. Basically, it will kind of replicate the same element all across from one element to 3522 elements. So you have a %0 with that broadcast, and these are all your SSA names. You do a div with the arg0 %0, broadcast again, mult and cast, and then add, and then return the final value. So this is the first level of MLIR that you get into from your data flow graph, right? And from here, the journey starts for the compiler to take this data flow graph. And finally, I'll be generating ISA for my Habana accelerator. Actually, it is an XPU. So truly speaking, it can generate various other kinds of ISA. So this is the first level. Now, what do we want to do? As part of the compilers, you may know, you're doing LLVM. At various points of time, you need to figure out, well, I have this loop, I have this instruction, how much time it will take to execute, right? How much time it will take to execute? What are the overheads? Am I going to get bound because of my registers that I have on the system? Will I spill? Various kinds of almost hardware level details that you want to know, but without really, compiling the full thing and then running it and actually collecting that data, right? So for example, if you want to know runtimes, you actually need to run your program. Otherwise, how do you know your runtimes? But there are certain characteristics which you know when you actually generate the full code. For example, if I want to know how much registry usage has happened in my code and are there been spills, if there are spills, how heavy are the spills? This you can figure out by just looking at your output code, right? Things like that. So there are both aspects, like inside the compiler, while you are compiling, I want to know certain hardware characteristics, right? Without actually running the program or without actually compiling till the very end. Now, LLVM already provides a mechanism for that, right? So many of you are familiar with TTI. So the TTI is LLVM's mechanism to approximate that. So mainly what you do, for example, a very popular thing that we do is, let's say, loop unrolling or vectorizing. Let's take vectorization. Like I take a sequential piece of code and I want to vectorize it. And then after vectorization, I really want to find out that will this vectorization finally help? Or am I going to get similar or slower code? Like unless I am 20, 30, 40% better than sequential code, it may not make sense to vectorize. So how do I do that? So I take this sequential piece of code, let's say a single number of basic blocks inside a loop. You take the sequential instructions and you just take the TTI numbers, keep on adding them, and you get a value. You have a vector plan or V plan, you vectorize it, and you keep on adding all the vector instruction and you get a value and you say, yeah, this looks like, okay, I'll be so much percentage better. And if it's not better, if it's close within 10%, let's say due to some reason, you may just abandon your vectorization. Now, these are good, but obviously they're not perfect. And if you are in machines which are doing out of order, which are doing various, our modern machines are much more complicated than this, sequential piece of execution that you are assuming. You may get, wrong results, or you may even make wrong decisions. And if I take that to the level of, ML frameworks today, it is much more complicated because I am dealing with operations at a very high level. If you look at div or a mult, actually it's operating on a tensor. And then if you visualize that, it mainly becomes, when you are synthesizing this operations to actual code, it basically is a bunch of loops operating on all the dimensions of this tensor. So it's not as simple as saying, I'll just add some value, I'll give it some value, and I'll add up this, all these 6 instructions that are there, and I'll give you some value for your runtimes or some other stuff. It's not that easy. And, creating TTIs, it was okay for LLVM because LLVM-IR kinds of has a unique format, but with various dialects that have kind of explored, I really cannot provide, or it's not a good idea to provide TTIs for all kinds of, like every time I'm in a dialect, I want to query and say, tell me how much it takes, or what's my register pressure going to be? Can you tell me? And it's not that easy. So what's the solution? The solution, what we have been looking at, and I think you would have seen some work happening over the last few years, is to do ML, at least from our side, to do ML, we are actually using ML itself to do some of these predictions, right? So what I want to do is, I'm given a graph at a very high level of dataflow graph, and I represent it using MLIR. And from this MLIR, I want to predict various characteristics of what will happen when I run it on a particular machine, be it CPU, GPU, FPGAs, or AI hardware accelerator. So this is the top big problem. Okay. So next slide. So some of these I've already talked about, but as you can see, the MLR dialect here that I have described is actually currently is a proprietary dialect. We have not exposed it anywhere. But if you are familiar with the dialects, it is similar to a dialect called MHLO or TOSA. MHLO is currently kind of probably is going to be phased out. It is from Google's Tensorflow. If you know about the Open XLA project, where they are trying to bring together certain aspects of these things called MHLO and LHLO into an open XLA open source work. This is like a high-level representation of your operators. And if you know about TOSA, TOSA is from ARM. So they also kind of, you can go from your Pytorch TensorFlow programs to TOSA, and then from TOSA you can lower all the way down. So the level of this dialect is similar to MHLO. Doesn't mean the work that I'm going to describe is applicable only to that. I'll tell you about certain things, and remember, remind me of this if I forget that. As I go forward, that this, though being described for high-level MLIR, is not necessary to be used only in high-level MLIR. We can go at various levels. Okay. And then, given this, what I'm trying to do? What I'm trying to do is I want to predict various hardware characteristics. So it can be register pressure, it can be XP utilization, it can be various other things. So I'll mainly talk about register pressure in this particular piece of work, but we did for both register pressure and XP utilization. And when I say XP utilization, it's mainly like, in terms of your code generation, how well are you utilizing your ALU resources, vector resources, vis-a-vis, doing memory and other kinds of things. Okay. And this can be extended to other hardware characteristics like total runtime or throughput. Now, actually, we have been doing some work with total runtime. It is not as successful as the register pressure XP utilization problem, and I'll tell you why that remains a bit of a challenge. Okay. Any question till now? It's a very, very high-level description of the problem. Okay, please stop me whenever you want. Yes.
So this is about prediction of the characteristics before running the program, right?
Exactly.
The problems.
Exactly. Yes.
Okay.
Yes. And many cases, it's not even just running; it's not even compiling. Right? We don't want to compile it.
Yes, compiling.
Yeah, it can be both. It can be compiling. It can be yeah. Okay. So once again, as I said, one is you'd require this. So this is a problem, and what is the real motivation of this of doing that? I mean, people who are deep into compilers will understand the motivation immediately for at least, let's say LLVM-IR, as I said, for vectorization or loop unrolling or doing some kind of scheduling or things like that. But from an ML standpoint, right? From the ML standpoint, LLVM is really very, very far down the pipe. We are at a dataflow graph level, and we go through various stages before we even generate LLVM-IR for our hardware accelerator, or let's say for a GPU, if you generate SPIRV for a GPU. It's like very far off. So even before that, you need to do a lot of things. And we still do, we still do unrolling, we still do various kinds of things. We still loop interchange and blah, blah, blah in this high-level MLIR. But one of the very well-known or popular things that ML dataflow graphs or ML optimization does, and it's like, the first thing, if you're developing an ML compiler, this is one of the first things that you will be asked to do or look into, is something called fusion. Now, all of us probably are familiar with loop fusion, traditional loop fusion that we do, but here it comes up to what is known as the operator fusion, right? Because these are, operators working on tensors, and the idea is very similar that I don't want these tensors, maybe many of these tensors are very, very big in size, okay? If you know about, all the GPT, they tell, okay, this many parameters now, this billion, 170 billion, 200 billion, and talk about these parameters, right? These are nothing else, but you will see that some of these are nothing else but the sizes of the tensors in some form. Okay, it's not just a single tensor, but many of these, what you call as weight matrices of the matrix multiplication, which forms the core of your ML data flow. So as you go further down in the AI pipe and look at this, bringing these tensors to and from memory is very, very time consuming, obviously, and we don't want to do. We want to keep them in our caches or local memories or whatnot, software-driven caches as much as possible. So you'll see this fusion is a very, very important optimization in the ML compiler framework. These are called operator fusion. Finally, this operator fusion may boil down to loop fusion at the back, not necessarily, depending on how you are implementing your ML compiler. If you're doing at a very high level dialect, it need not be loop fusion. In our case, actually, it becomes loop fusion because we lowered this top level ML to something called affine dialect, which is nothing else but affine loops. And then we use the traditional affine loop fusion available in the ML pipeline that is available today in MLIR to do the fusion. So let's say I want to do fusion, right? And so when I'm trying to do fusion, let's say I have this dilemma. I have this dilemma that, let's say all of these are fusible. That should I fuse everything versus I fuse a part of the graph, right? As I said, assume that everything is fusible. Now, people may ask why, if everything is fusible and you are saying that keeping in memory is bad and fusing is better, why should I, do partially rather than do the full thing? And the answer is pretty simple. The answer is it depends on your hardware. Because, when you are doing some of these things, finally, when you are generating code on your ISA, it creates a lot of, like, for example, if you are normally also fusing in an LLVM, you are just increasing the body, right, of your innermost loops in some form, provided it's doing inner loop fusion. So as you increase the body, very simply, the first thing that will come to your mind is, okay, I'm increasing the body, which is good, like in loop unrolling, but at the same time, I'm creating register pressure. And then for, let's say, our Habana hardware accelerator, we have a very, very strict rules about spilling because our spill area is very small and we cannot spill beyond that. We cannot really spill to the main memory like in the CPUs. So what happens as a result is we have to be very careful about how much fusion we can do. So if you're doing hand fusion, let's say this operator fusion is done by some users by hand by writing some kind of kernels. It's easy because they can say, oh, I'm now using, they can compile multiple times. They say, oh, I'm using like 20 registers, 30 registers and beyond. Like we actually have 40. We have actually 45 vector registers. So after that, we start spilling, and after some time, we cannot spill further. I mean, if you cannot spill further, our code will just run out of spillage area, and we'll just say that you need to break down your kernel further because we cannot compile. So this is a thing that we need to decide at a very high level, very, very high level, without even doing the full compilation, right? And I'm trying to take the decision on should I fuse full graph or a subgraph or a few elements of the graph, and then I need to answer certain questions about the hardware before I can go and proceed. Okay, so that's a simple thing, right? Because at the end of the day, you have your high-level MLIR code. So this is basically the flow, right? That's happening, and you can now visualize the total flow that's coming from the high-level MLIR all the way down to your hardware. You have your data flow graph, right? And that data flow graph is represented as a very high-level MLIR. And then you have your optimizing compiler. Now, when I say optimizing compiler, this is just not LLVM. We have our own ML optimizing compiler stack, which actually finally gets to LLVM or SPIRG, but it's an optimizing compiler stack consisting of various parts. And first part is that first part of that optimizing compiler is full MLIR compilation stack. Now, at this point of time, somewhere in between here, we have to decide, hey, should I take this full graph or should I take part of this graph? And for that, I need to predict, hey, if I am going to compile for Xeon versus my Intel Arc GPUs versus some FPGAs versus some Habana hardware, what's some of the hardware characteristics that I have which will allow me to fuse everything versus a subgraph versus something, right? So I have to answer questions in between here about the characteristics of this hardware platform. Without going through this entire chain, you can see, once you generate the code, you can answer certain questions. And obviously, when you can run, you answer furthermore questions. But without doing this full arrow all the way down, or doing this full arrow all the way down, I want to answer my questions here itself. So obviously, these have to be approximations. We cannot answer it always correctly or always properly. And for those approximations, we'll see that how we will try to use ML itself. So if you see, this is an ML pipe. Today's ML compilation pipe, and inside this compilation pipe, inside this optimization compiler, we want to use ML itself in another form to answer certain questions about my. So this is a very, very big motivation for us to do this cost modeling at a very high level. Any question before I go to the, are you all good with the motivation? Okay. So yes, once again, stop me, if you have further questions. So what is the overall ML-driven architecture for this kind of problems? So what we do is, and this is a very standard, and people who have done ML, it's not new to you at all. We still do supervised. We are not doing anything unsupervised for at least this particular problem that I'm trying to tackle. So I have my MLIR training data set, which is nothing else but many, many input data flow graphs. Now, as you can well understand that this area is still it's a very early development stage. People have been doing ML compilers now for 5, 6, 7 years, but using MLR is just, and that too in the ML compilation framework, as I said, is about 3, 4 years. And for us, in our Intel Habana compiler stack, we have been doing it for the past 3 years. So this training data set is not very huge right now. It's on the order of thousands. It's not even in the order of 100,000s. And you may have some people who know ML in detail may know that if you have smaller training sets, your accuracy and other things may drop drastically. But yeah, I mean, see, we have to start somewhere, right? So when we actually started, when we started developing this framework, actually and we try to develop it for fusion. As I said, that we want to answer some questions about should I be able to fuse this or not, and answer questions about the hardware. We had about only 2,000 such graphs, just 2,000. And obviously, as you said, as I said, that 2,000 is not good enough for doing good predictions, especially if you're going through a deep learning model. And so what we did was we tried to augment these training data sets. We tried to combine. So if we got 2 data flow graphs, we tried to combine them together to create a bigger data flow graph. For the bigger sets, we tried to split so that we created this new data flow graph. So these are like auto-generated from these augmented data flow graphs is auto-generated from the original parts. And so finally, we had about, after doing this and doing some sanitization and other stuff, we had about, I think, 20, 25,000. That's where we started. We felt comfortable that, several tens of thousands is a good starting point. And as I speak today, I actually have a new set as late as last week, which is about close to 75,000 training data sets after the initial set and the augmentation, which looks pretty good. So what happens? So we have this data flow graphs as MLIR, and we have our model. I'll tell you what the model is. We have our model, and we also have our final hardware. So here it shows Cascade Lake, which is our slightly older. We are now into something called Sapphire Rapids. This is on the Intel CPU side of things, but in general, my own area of work is mainly, if you replace this by Habana hardware, mainly what we call as Gaudi, which is the Habana training accelerator. So what we do is we take this and we go through the framework that I showed you here, right? You go through this full chain. You actually go through this full chain and actually run them, compile them, run them on the hardware, and observe the various characteristics. It can be your register usage, register spilling, actual run times, utilization of the various vector units, ALUs, and things that you can just, we get those kind of data from some kind of a dump from our as you compile and run them. Okay, so you have this training set, you get all the data for those training set, and you now build your model, to fit based on whatever hardware characteristics you want to predict, and you see the loss, you do backprop, and this is a general, all of know the very famous ML training cycle for supervised learning. Now, especially for ground truth, it's not always necessary that we are able to execute them because let's say for a hardware which is in prep or which is not being out yet. For example, we are on our second generation of Gaudi accelerators called Gaudi 2, which is out, available, but we are working on the next gen called Gaudi 3. And then Gaudi 3 has its simulators, but we still cannot run it on the real hardware, but it has its simulators. So obviously, sometimes we may need to collect this ground truth or observed characteristics through the simulator and not the actual hardware, where things can be slightly different from your simulators because it may not be able to run big piece of code and things like that. So anyway, so to come to the actual story, so this is our normal training cycle, and the input to our training cycle are these high-level MLIR data flow graphs. And our hardware ground truth or observed characteristics are the things that you get by actually compiling through this arrow path, actually compiling them through our compiler tool chain and then observing those characteristics on those path. Okay. Right. Now, regarding the training data set, now people may be starting to wonder that, okay, we have an MLIR data flow graph, but then how do you really input it as an input to the ML framework? Because these are all code, right? I mean, it's like LLVM-IR. How do you input all those kind of things? And the answer to that is we visualize or we use the MLIR code as an NLP problem, right? And so, NLP is something I am hoping that in today's age, all of you are familiar with, especially because of, as I said, ChatGPT and the GPT-like, large language model systems. That I just look at my MLIR data flow graph as a bunch of tokens or like an input text, right? Nothing else. So what we have is the input, and I'll tell you how we are going to visualize them as tokens, but just think of it as like you are giving a set, asking a question or in typing something in your ChatGPT window and getting a result, right? This is almost an equivalent of that in some form. We could have actually even used something like a transformer with GPT for this particular problem, though it will be too heavy duty. Most likely it's not, we need not really use such a sophisticated model, but the basic structure is the same, that we visualize. So if you look at, I'll go back all the way to this code. If you look at this code, I'm going to look at this code as simply a stream of text tokens. That's all what I'm going to do. Just look at it as a stream of text tokens, right? Okay. So now coming back here. So what I do is like look at this code as a stream of text tokens and use these tokens in some form to do some kind of encoding. And I'll just go into, if you're not familiar with encoding, some of you are already familiar with encoding, that we'll do some form of encoding. We'll do what is called as embedding. And then we'll actually be inputting that to the model. Because if you just give this code, a model obviously will not be able to understand like what is being fed to it. So I have to break down my MLIR sequence into some understandable form and some understandable representation that a model will be able to ingest, right? Okay, so as to go further into it, as I said, the input is a sequence of this ops, and the input-output tensor shapes. Not everything in the text token sequence may be taken. Some things we may drop, like let's say brackets and things like that, but this may still be used in some form. And what we do is we create a CSV file out of it. It's a kind of a database, kind of basic database consisting of your MLIR text sequence, your input-output tensor shapes, and finally, for your training data set, I also want to put in what is my target variable, right? Is it register pressure, XP utilization? What is my target variable? And we actually did, several kinds of text sequence encoding. I'll talk to you later about that as to what exactly we do in these two kinds of CSVs. Currently, I set to 20K. I didn't update the slides because, as I said, I got a recent set of MLIR files where I'm at about 75K, but we haven't still experimented down the pipe as to what the results are. So this result that I'm going to show you has been created with a training data set of about, I think it was 22, 23K. And we actually did partitioning of that data set for our validation and test. So actually, frankly, at the end of the day, we were training with most likely close to 17, 18K only, and not 22, 23K. Okay. So let me, before you ask the question, let me explain this slide, and maybe I'll stop for well on time. So I'll stop for maybe a few 5 seconds or so to ask whether you have any doubts on that. So what do we do? And when you get an MLIR sequence is, as I said, these are all our tokens, right? These are normal text tokens. And the text tokens are interpreted in various formats. So these are the formats that we interpret as. One is our input, what we call as the input tensor shapes, right? There's a special term that you will hear a lot in the AI world, especially for people who do ML framework optimization. So these are called tensor shapes, and input tensor shapes, and then the output tensor shapes. So these are two different kinds of tokens that we generate. For the input tensor shapes, once again, and this has a very what I'll say important connotation at this point of time, that we consider this full sequence, like if you see this, right, for the first tensor 64 cross 128 cross 1024, which is mainly a 3-dimensional tensor of type BF16 as one single token. Now, people may ask that why should we do so? Because these are individual elements, and maybe we should tokenize them further, which is absolutely fine. And I'll go into reason later as to why we are not doing it, and even, what are the challenges. So currently, let's look at it this way, that these are our input tensor shapes, and each tensor shape is one unique token. And then you have our output tensor shape. Output tensor shape, usually we send out only one tensor, but there may be cases where there's no restriction that we cannot send out more than one tensor. And then the opcode sequence representation. This is a very important part of your sequence representation. Like, what is your sequence representation? So right now, if you see, it is fully tokenized. Forget about the, currently the opcodes also tell you what is the output type. We currently ignore that. Once again, we can use it in some form, but currently it's ignored. So you'll see that %0 equal to add arg0, arg1 is your full sequence. We add some delimiters because we have a new line. We don't use new line. We have some hashes, and we keep on adding all the other sequences of your opcode. So at the end of the day, you'll see the full opcode here will be tokenized in this form on the right. And then we combine all of these three things. So these are three important things: the input shape, the output shape, and the opcode sequence as tokens. Now, if you look at this once again on the left-hand side, because XPU is just a dialect, currently, we don't add XPU to the token sequence. You can use it. It doesn't matter. But if you look at it, this is the sequence representation we have. We actually put, though these come first, we actually put the body first. Okay, here it is just 3 adds. And then we have the input shapes, and then we have the output shape. And this is just a linear chain of tokens that we have. Now, interestingly, that's where I'm going to tell you. Interestingly, we have 2 ways of looking at it. One is in the first tokenization, in the first method that we tried of tokenization, we actually just ignored all these arguments or opcodes. Okay, so we just said that, okay, this is my MLIR piece, and I have to, project or predict what will be my register pressure, how many registers I'm going to use, or XP utilization. To simplify things, I don't even add the arguments. I'll just have the add sequence followed by all of these things. So just to see that what is the impact of a kind of a minimal representation of this? It's almost like a minimal representation of your input MLIR. So what happens as a result? And then in the next sequence that we really did add the arg0 arg1s and then tokenize them. It did also put them into our token chain. Okay. So I'll stop here just to ask that, are there questions here? Are you following? Are there issues regarding whatever is presented till now, at least on this side of things?
Yeah, so there's actually a question on chat. How does the feedback work for loss function or error computation? Is the program run, or is there a static estimate for this?
Yeah, so see, if it is only for register pressure or XP utilization kind of thing, we don't run it because for register pressure and XP utilization, we can kind of get it, especially from the Habana side of things, we can get it from our executable itself. We don't need to run it. But yes, if it's like a runtime that we want to predict, we will need to run it. Okay, any other question?
Sir, I have a question regarding this. So, we are currently the register pressure is being predicted. So, whether the vector registers are only considered for this case, or
Yeah, so if you, I didn't go into the details of that. For our Habana accelerators, everything is mainly working on vector register. So it's almost like everything on the vector register side. But if you are, let's say you want to do it, you want to run this on your CPUs, right? Mostly what happens is, especially for ML ops, most of these ML ops are generally vectorizable. So you will be using a lot of vectorization. If you are on the Intel side of things, you will not only use, let's say, AVX 512 or something, you will also use something like a VNNI, which is a neural network intrinsics for, kind of instructions. So you will be using a lot of vector registers. But whether you are using or not, in cases like here, for example, as I said, it's like for us, it's a unique prediction for vector registers. But if you are on a CPU, which is a mixture of scalar and vectors a lot, you can actually predict both of them. It's not just you need to predict a single one. You can predict, several register types. And then you can have loss functions, kind of a categorical loss function on them and things like that.
Thank you. Another just minor point. So, does this vector registers also have different classes for which this register pressure is being predicted?
Yeah, come again. Is it register classes?
Register classes for vector register are different classes may be possible for the vector registers even, depending upon the size of vector registers. So, are we like in this work, is it that is also considered as
No, see, currently that's not done. As I said, mainly we were looking into our Habana AI accelerator system, which is our vector registers are fixed length. We have actually 2048 sized and a big size vector register. So we didn't consider that. But as I said, you can tweak your model to predict your classes plus your pressure. It's not necessarily just be one type. It just depends on what, because when you're doing a training set and when you collect the data from your executable, okay, or even runtime, let's say executable, you can scan your executable and find for each class of either scalar, vector, whatever registers, what is the amount of usage and what is the amount of spills that are happening. And you can add all of them to your prediction class, and then you predict accordingly. I mean, it's all doable. Right now, we have a kind of a single element predictor in terms of what we are doing, but it need not be that way. Okay. So we may have to tweak with the models if you have to generate for each class and each class type, how much is the usage and how much is the spill.
Thank you, sir. Thanks. Yeah, I have a question regarding the opcode sequence representation. Can we represent fused operators also in the same way as these preliminary add operators are represented, or do we need to do something extra for operators that are fused?
So it is all depending on what is your training set. So we really don't have any bias towards that. I mean, the thing is, you have to have your fused operators in your training set. Okay. So in general, if you have fused operators in your training set, so mainly at the end of the day, we need to tokenize and embed. And if you don't have an embedding for your fused operator, obviously later your inference will go for a toss. So we can support everything. There's no problem. I mean, as such, the mechanism doesn't preclude using a fused operation, but if you should make it make it possible that they are part. At least you have a reasonable number of data flow graphs having fused operators in your training set.
Yes. Thank you.
Any other question?
Yeah, so there's.
Oh, sorry, go ahead, Jill.
Yeah. The representation, I see the high dimensional tensors, right, Dibyendu? So if we do not have these high dimensions, many.
Yeah, I'll show you that.
Right,
okay, yeah. Go ahead. If you don't have the high dimensions.
Yes, if I don't have high dimensions like scalar code or text processing applications, how and also the sequence of operations, whether it will come as the program, how the .s file will be.
Yes, so there
IR.
are papers. So I'll just really refer to you to some papers, doing that. The first work which kind of talked about this kind of things of tokenizing executables and stuff like that. You find a paper is there in the reference at the end. It's called Itamal from Charit Mendison team from MIT, where they actually tokenized x86 instructions. Okay, so mainly the assembly. Now you can think of a similar thing that you want to do for LLVM-IR, and I know Professor Ramakrishna's team and Venkat and others. I mean, they have worked on what is called as IR to VEC, which is literally taking LLVM-IR and getting high level, vector dimensions for these IR, similar to what to VEC that we do in NLP. You can do any of those kind of things, right? You can do any of those kind of things. And even if like there are no tensor shapes, it's like normal LLVM-IR or even like an AST, there are work that has happened on tokenizing ASTs and stuff. So there has been quite a body of work on the software engineering side, for tokenizing. For example, any of these you can see today that that will do next filling up prediction for your editors, and even from ChatGPT, which are completing code completion kind of sequences, will all be working on some kind of high level AST representation of your code, and that has been fed to a transformer model, and they'll predict from there. So I'm stating a very simple model mainly because because I'm working at an MLIR level dialect for which there is no already present encoding. Like if it was LLVM-IR, I have done actually experiments with Professor Ramakrishna's IR to VEC. So if it's like LLVM-IR, I'd probably just take that encoding or embedding and start working from there instead of trying to do this kind of stuff. But if you have, if it's LLVM-IR, I'll suggest go and do IR to VEC. If you have x86 ISA, maybe you can look at Ethamal or a new paper called Granite, how they are doing that tokenization for that. So these are like probably standardized stuff. You can just pull things from their Git and do it. But if you are in your own MLIR dialect, as part of your own MLIR compiler tools and system, you cannot use any of these things. Or you are doing something. Let's say you do have your own some parsing sequence. You have an IR which is like proprietary IR. So you have to do something like this. You have to do some kind of tokenization. Now, what is the level of tokenization? How far you will break the tokens? It's all up to you, and that will be kind of, a bit of an experimentation that you have to do.
Yeah, thank you for details. Yeah. So this is primarily for high dimensional vector data, right? Yeah.
Yeah, but as I said, once
Yes,
again,
yeah,
this can
correct.
be tailored to various things. I mean, we can do various things. Yeah. Okay. Let me go to the next slide. So once you have this kind of tokenized sequence, this creates actually a very sparse vector representation. And people from the ML side would know that sparse vector representations are not good, and we need to have what is called an embedding, which creates a dense vector representation. And we usually do, maybe 100-dimensional, 64-dimensional encoding. We don't go beyond that. I think it's 64 right now, kind of misses. Because that kind of encoding was done some time back. So this is very, very similar to what to VEC, right? What happens with this kind of vector embedding. Now, there are two ways of doing this kind of an embedding. We can do it offline or we can do it online. What I mean by offline is I do some kind of either self-supervised or supervised learning and get an embedding for my MLIR dialect. And then every time I see a sub, I see a broadcast, I get a mult, I just, from a kind of a dictionary, I pick up that kind of an embedding. Or I can do the embedding as part of my, every time I train, I do that embedding. So currently, to keep matters simple, because we don't have a self-supervised learning mechanism, the embedding happens as part of your training. So someone asked about whether I can have a fused operator. Yes, you can, because what we'll do is if you have a training set with fused operators, once you start training, the fused operators will start to have their own dense vector representations, right, which you can use later. Now, if you look here, right, so let's say I have this kind of a token sequence, right, and this tokenized sequence will get some numbers, and I can see that the tokens which are the same will all get similar numbers. And these tokens will, finally, each of these tokens will have a representation in your 64-dimensional or 100-dimensional or then 300-dimensional vector space. And all of you who are familiar, as I said, word to vec, this is what they say is like when you take your, let's say, 100K words in your English dictionary, it's not that it's 100K words, but each word, once they do this kind of a self-supervised training and embedding, each word will get a 300-dimensional, let's say a 300-dimensional vector. Now, what that vector represents, no one knows. Really speaking, no one knows what that vector represents. But if you now map that vector, 300-dimensional vector, and do kind of a TSNE mapping of that vector, you will see that concepts or words which are similar in various ways will be very close to each other in your vector space. For example, let's say, animals, words representing animals will be close to each other compared to words which are materialistic. Okay. Similarly here, a sub, if you have the vector mapping, the subs vector mapping, right, in the space, I think the light is going down in the room. I'll just turn on the light. Just hold on. Okay, so So if you see sub, add, mul may be close to each other compared to broadcast or cast or whatever it is, because these operators are far off in terms of what they really mean. Okay, like square root may be closer to the, someone like other operation like an R square root of things, but will be far off from, let's say, a sum. Okay, and you do the mapping, you can see that how these operators are, close to each other. Similarly, for the higher dimension, and this kind of tensors, you expect tensors with similar sizes, like 1 cross F32 will be close to, let's say, a 2 cross F32 or a 4 cross F32, and far off from this kind of a bigger dimensional tensor. So that's the expectation once you do the training. And as I said, if I have 20K training set versus a 50K training set versus a 100K training set, this embedding becomes better and better, and the vector representations become better and better because it learns much better in terms of what it really means to have a 3 cross 360 F32 versus what it means to have just 1 cross F32. If you have a bad training or bad embedding, they may lie close to each other, and then when you are doing prediction, you will actually have results which are very, very approximate or way off from the real prediction that you want to see. Okay, so now let us get into models. Okay, so we went through various things. We talked about the input MLIR code that we have. We talked about how we'll do the tokenization of that MLIR, how will you do the encoding, how will you do the embedding, and then finally we need to have some language model which will be able to understand this and create some prediction for us. So if you look at on the right-hand side, this is a very top-level view of how the model looks like. So you have your MLIR code, you do your encoding, and then you do your embedding. Once you have your embedding, basically once you have your embedding, we have this, our model is ready to be fed into, our input is ready to be fed into the model. Now we have restrictions on the sizes. We cannot take, let's say, a very big input tensor file right now because it's very similar to what you see in once again in ChatGPT. All these language models have a restriction on the size of tokens that it can take in. It's not infinite. Most likely you'll have a certain sequence and then you'll get an answer, and then again you'll put certain sequence in the answer. So here similarly, our because it's also very high level MLR, we really don't have 1,000 lines of function. It's not like normal C++ code where you'll put the entire code in and you'll see like 1 million lines of code, right? And if you go to IR, it will be like several million. Obviously, you cannot put several million lines of tokens into a model and get output. Most of the models right now, at least NLP models, cannot cannot handle that kind of size. So you have to restrict. In general, if let's say you have to do if you are in LLVM-IR, you have to do a basic block, maybe at most a function with several thousand tokens, maybe several 10,000 tokens, maybe not more than that. So here we have a restriction on the number of tokens that we can feed in. But in general, it's okay for us because, as I said, we are at a very high level MLR. The data flow graphs which we want to fuse are pretty much restricted in size in terms of how big they are. Now, once we have that, we tried various models. So initially, we tried very simple models. We tried just simply fully connected layers, MLPs and things like that. But we saw that the errors are pretty high in terms of. So basically, we are just talking about register pressure heuristic. We tried LSTM, which is a kind of recurrent. And then finally, we tried something which kind of borrowed from convolutional neural nets, but it's not meant for images. As you may know, CNNs or the conv nets are usually meant for images, but we use, and this is a technique that people usually use before LSTM became popular, or even transformers became popular, is people did a one-dimensional convolution on your text. So basically, you will have a small window, okay, and you pull the window across your text. Right? It may be, and these windows, we can have many numbers of such windows, right? And we can then build stacks of these windows, similar to how you do CNNs, right? Maybe you have a filter. It can be a 1x1, 3x3, 5x5, 7x7 filter on your image, and then you move this filter across your full image, and then you can have many of these kinds of filters, and you can build stacks of these filters, and then finally you do your image prediction. So similarly, for text, so instead of doing LSTM and instead of doing anything simple, we didn't want to use transformers still at that stage because we tried a bit, but the results are not much better, and we didn't want to, because transformers are slightly heavier in terms of time. So we thought that using con1D, which is basically a single dimensional con, would work, and it looks like it does work better compared to many of the other models that we tried. So this is finally like the actual model that I'm going to talk about here. So this has 6 con1D layers of filter size equal to 2. When I say filter size equal to, and actually these I'm saying filter size equal to 2, we have played with many filter sizes. When I say filter size, because it's con1D, it's basically saying that I'm going to look at 2 tokens at a time. Okay. So this is kind of, if you like, increase it to 3 or 4 or 5, which we do when we consider not only the ops, but also its operators, because then it becomes bigger. The operator becomes bigger. We actually go to filter sizes of 6 or 8 and things like that. So we have this kind of filters, right? And you build stacks of them. So we have 6 con1D layers, followed by a single max pool. And then we have 3 fully connected layers, which actually will finally predict the register pressure. And this, as you can visualize here, I don't have an animated one, but this filters, mainly this filters, of size 2 will move across. So this is your full sequence. It will just move across your sequence, right? Every time it will move once and look at 2 tokens together, right? Like you do in convets. And then you have many filters of this kind. And we built 6 stacks of them. So what we see is, we get pretty good results. The RMSE, or the root mean square error that we talk about, mainly in terms of what is the error you get from your actual register usage that's happening once you compile versus what you are predicting, is within plus minus 5%. And if we also did some initial work with XT utilization, we saw that our RMSE is pretty close, once again, close to within plus minus 4% of the actual XT utilization that is that we see in the hardware. So any question on the model?
Hello.
Yeah.
Am I audible?
Yeah, sure.
Yes. So good evening, sir. I have just a basic question. Like, suppose if there is introduction of any new hardware, like specialized TPU or GPU. So with the introduction of the new hardware, just to make a prediction, do we need to change the number of parameters that we are using in our ML model as to cope up with the new hardware? Or in other words, just to frame the same question in other words, how you ensure that with the same set of parameters, you can make the right prediction for any newly introduced hardware? Thank you.
So there are 2 sides to the thing. So obviously, if you have new hardware, the same model may not work well. So there are several ways people look at this problem. And we have also looked at the problem in the same manner. One is called, very well known in ML literature, called transfer learning. So what we do is, we probably will still have a similar model with con1 max pool and FC. The basic model may still remain the same, but then we may need to change the layers. Maybe we'll change the filter sizes. Maybe we'll change the number of layers. Maybe instead of 3 FC layers, we'll put 5, or maybe reduce it to 2. And then we'll see that how the RMSE varies for the new hardware. Okay. So this is called transfer learning, because I've understood that for my Habana accelerator, this works well, and I'm going to just change certain parameters. So once I change the model, I'll need to retrain, right? Because as you also understand, let's say the number of registers that's available from hardware X to a new hardware Y might change. Let's say we had 40 vector registers earlier. Now maybe we have become 50, or maybe we can become 35. Who knows? Because of some other reason. So we need to retrain. Definitely, we can do a retraining just like that without changing anything. maybe that's what you will try first. Like take just the old model, take a new data set because you run it on this new hardware, and just retrain it and see what's happening. Let's say, maybe plus minus 5% has become plus minus 10% because you are now new hardware and the model is not doing as well. So once you see it becomes plus minus 10 instead of plus minus 5, I go back and try to tweak the layers and see, okay, from 6, let me go to 8, let me go back to 4. And this is just, it's experimentation. It's an art. There's no real science behind this, and everyone is doing this. And once you do that, you'll see, okay, how can I come back to plus minus 5? Or am I doing better than plus minus 5? So that's usually the way people look at it. Now, it can also happen that once you get a new hardware, now, just to rewind back a bit. So if it is totally different hardware, let's say it's not my next gen Gaudi of Habana accelerators, or from this, I take this and I try to say, oh, this is working well for some Intel X CPU. Let's try on an ARM CPU. Maybe it will not work well at all. Okay, maybe you have to change the model totally. I mean, it should not be that way. Our guess is it should not be that way. It's just that, as you are also guessing, that we may need to just change or tweak some of these parameters, retrain, and we should be good to go, and we should be able to hit similar numbers, but we cannot guarantee, right? And so maybe in some cases we have to try a different model totally. If you have a totally different hardware, we may need to try a different model. Okay. So does that answer your question?
Yes, sir. Thank you.
Any other question on the model? Okay, so
one question. So initially, in the previous slide, you mentioned it is whether CPU, FPGA, or an accelerator. So that information where we have in the model, Dibyendu, maybe
so here, so one is two things. One is in the model itself, you can provide some auxiliary hardware inputs, right? While you put in the model. In our case, we did not do it because right now, though we are saying it can be used, we did not run on multiple hardware. We mainly concentrated, at least for our initial POC, on the Habana accelerator. But it can be either encoded here, or if you want, you can actually build separate models for your separate hardware. It may be, as I said, it may be similar, but will not be the same. It is a kind of a transfer learning that, okay, once you run it on one hardware, most likely, similar kind of models will work well for the other hardware. But it did not be, as I said, it may be a different model, or if it's similar model, then you can give an auxiliary hardware input. So usually auxiliary hardware inputs will work well for like Gen 1, Gen 2, Gen 3 of similar hardware. But I personally think that if it is like totally different, like a CPU versus GPU versus FPGA versus the Habana accelerator, may not be just this may not work because you may need to change some of your model details in terms of number of layers, the filter sizes, and so on, which you cannot do by changing this, right? So I'll guess in that case, you will have not the same, but very similar models across your hardware.
Yeah, thank you.
Okay. So this is the model, and then I'll show you some chart of predictions, like what is the predicted versus actual register pressure. So when we tried, we saw that for about close to 20% of cases, we actually predict the exact same number of registers that the final program uses. For about close to 50% of the cases, we have only difference of one. That is, we are one register off plus minus one from the actual register usage. And then from 2 onwards, you will see that it decreases substantially. So between 0 and 1, that is, we just have such a small difference, we are already covering close to 70% of our predictions. And then 2 and 3 and lower below is just decreasing. So it's fairly good in terms of what we did. And this, let me remind you again, this was with just the operators being encoded. We didn't even encode the operands. And it's a bit surprising, it may be a bit surprising to many of you guys that what's going on here. I didn't even encode the data dependencies, right? Because, for example, for scheduling, register allocation, all of these things, we do all this liveness analysis, we will do all these calculations of interference graphs and all this kind of things. I'm not doing anything. I'm not even putting my, input registers, output registers. Input is, say, virtual registers, output is virtual registers. And still, it's able to do a pretty damn good prediction of the actual register pressure that's happening out there. And it's surprising. I mean, and for us, it's actually a very restricted program because ML data flow graphs only have, for us at least, certain kind of representation. This is not going to be true for if you are just trying normal C++ LLVM-IR. I'm very sure of that. But still, it may be pretty good. Like I'll suggest to you use, maybe if you're in LLVM-IR, try something like an IR to vec to register pressure, or some machine IR to vec to register pressure, and probably you will be seeing pretty good results even with very, very simple representations, tokenizations, embedding, and sharing. Okay. So the next one that I promised that I'll tell you is we did two kinds of, as I said, two kinds of encoding, right? One is we didn't take the operators, but not the operands. But then obviously, we expected that to be of lower quality, which actually is. And then you add the operands to the operator sequence. And we do get much better prediction, not only just the operator, but the operator sequence. But once again, what happens is, the reason why we tried also with that is, moment we add the operator sequences, our sequence will get much longer, right? The number of tokens will almost on an average increase by 4x, because you are adding all the operands now. You are adding at least two operands on the left, one operand on the right, and things like that. And so the training time becomes much slower. You are not even training on the GPUs at that stage. So training time becomes much slower. And what we found was the filter size of 2 was not good enough, because we now, in a single instruction itself, we have much more tokens. So we tried much bigger sizes of filters, like 16 and 8 and things like that. And then finally we went to 2 and 1. So there are some challenges here. I mean, for people who are familiar with kind of NLP like tokenization, that we can have something called OOV, which is like kind of an out of bounds vector mapping, which means that right now, when we put this kind of arg values, right? We have, let's say, arg10, arg11, arg12. In general, they really don't have any meanings, and because we are just doing text encoding, they just get into the system. And then if you have an arg value which has not been seen in the training set, maybe because the training set did not have it, you'll have a bad vector mapping for that. But what we have seen is, in general, even if you have a few bad vector mappings and kind of take a default vector embedding for that, it really doesn't change the the prediction accuracy too much. And now, as you can see, that for the same kind of input sequence and training sets and all that, the number of times we have, like, if you see previously, you have like difference of 1 is 50% of the cases, and zero difference is about 20, right? Here you can see the zero difference goes all the way up to close to 75, and 1 difference is close to 20. So between 0 and 1 itself, we have about 95% of accuracy, almost close to 95%. And so you are like much better off, obviously encoding everything. Now, once again, there are various ways to, do your models. This is, as I said, we want to do a quick and dirty model, so that we wanted to see how good our prediction accuracy and things are. And my personal preference is, people who are very familiar with ML may want to contradict. My personal preference is, let's build easier, smaller models, rather than, we could have easily used a transform model here. Okay, but maybe it's too heavy duty for this. As we said, we tried some transformers, we didn't get much better results compared to what we use transformers with attention and stuff like that. We didn't get much better results. Obviously, with much higher training times, we don't want to go there. And the interesting part is you have the simpler models. It's not necessarily that going to, as I said, going to more complicated models. If you look at Ithamal, right, as I said, is a 2018 paper which tries to predict throughputs and latencies using for x86 ISA using LSTMs. They use kind of stacked LSTMs. We actually, our model is much simpler than it's not even stacked LSTM. But there are people who have used something like graph neural nets. Okay, you will see papers where even in Granite, which is a kind of next gen, model compared to Ithamal uses graph neural nets. And if you see graph neurals, what they will do is, if you look at this operator sequence, right, what we have here on this, they will actually model the use steps, right? Like percentage 0 here is used in this place, so you will draw the edge between instruction 1 and instruction 2, and you will represent each of these instructions by a graph node, and you have a graph neural net instead of a simple thing like we have with Conv and Maxpool. They have a graph neural net, and then you predict over the graph neural net. And my personal take is, yeah, but it depends on what kind of code you are running and what kind of approximation, what kind of accuracy you are looking at. It's not necessarily just that you use a more what I'll say powerful technique that you are going to get much better results. It may not be that way. So as I showed that in case of, at least for our stack, for simple things like register pressure or even XP utilization, I can do it. And this is extremely fast training because Conv1D are very fast over text. So we have extremely fast training, and the results are pretty good. So that's where, any questions up to this point from now? I'll just have some next steps and discussions in the next few minutes.
Hi, Didi. This is Venkat here. I have a couple of questions. Firstly, how do you calculate or characterize the register pressure at the initial stages of MLIR? Is it?
Yeah. Okay. So that's a good question. So for us, this basically in our system, as I said, once the code is generated, and if there is fill and things like that, we will get that data from our executable saying that we use so many vector registers, and and if there is no spill, the spill is 0, and if there is spill, it will tell you that how much of the spill area has been used. So that is pretty, that's something that the compiler executable throws up when we run it. When we compile it itself, it throws up that kind of information. So that information can be used at a very high, even we don't need to go to lower level of MLIR dialects. From this high level itself, we can do that. Are you looking for something else?
Yeah. So at the high level, do we even know or will be able to capture the register classes of variables? Is it possible?
Yeah, that's what I said. So currently in our work, as I said, our main goal is the vector registers, because that's the main important thing. We don't even bother about our scalar registers as much. So unless the vector registers, yeah. So that's why we didn't concentrate on that. But I think, as I said earlier, for your hardware, let's say you are doing x86 or some hardware where scalars, vectors, or even for vectors, the various classes of vectors are important. As long as you can get the data, so basically you have to do the compile, right? You have to do the compile, get the data, and if you can get the classes, then obviously you can build the models on a, let's say, on a per class basis, or with some tweaks of this kind of a model, which will say that this is what will happen.
Yeah, I got it. Yeah, thanks. And one more question is, do you have any limitations on the maximum length of the input that the model accepts?
Right. Currently, I think, I don't remember, I think the maximum token size set is probably 2048. Okay. So because, as I said, because we are representing the data flow graph, let's say even the data flow graph has, even if it has 200 nodes in the data flow graph, 300 nodes in the data flow graph, 300 nodes in the data flow graph will probably, create 1500 tokens, 1800 tokens. It's not like, as I said, not like, a big unroll loop in LLVM-IR. Okay.
Yeah, makes sense.
So that is a good question because see, our next steps, which we are looking at, is not just a top level MLR because fusion is done at this level, so it is good. But there are many decisions that we need to take at slightly lower level of MLR, which is basically we are at affine dialect. And you may know in the affine dialect, we'll have loops. We have much more code than what we have. And obviously, we have to take in at least, if not 1,000, 2,000, at least up to, let's say, 5K, 6K kind of tokens. Okay. So that's at that point, we'll see that whether, that is okay for our system. It is difficult because, as you may know, I mean, we really cannot take very big amount of token sizes because all this text kind of systems will not work. Right?
Yeah, makes sense. So, and that means that number of tokens that we encounter is also possibly smaller, something around hundreds. Is it a good?
No, currently it can see, as I said, currently it can go up to, I think the biggest we have seen is 1,000 plus. Okay.
I mean, the number of unique tokens that we have.
The number of unique tokens, that's a good one. I have to check that. Mainly the number of unique tokens will also, because we are encoding that's a good question that you put. So that's also one of the reasons why we did encoding of the full tensor. Okay. Because if you have a full tensor, what we've seen with the MLs is, ML frameworks is, many of these tensor sizes there are like popular tensor sizes. Like if you see any of these GPT transfer like system 768, right? Cross something is a very popular tensor size. So if you have really arbitrary tensor sizes and you are training or inferring over them, your number of tokens will keep on changing. Right? It can really go up very high. And that can cause problems. We tried thinking of doing as I said, let's say on an individual number basis for the tokenization. But if you do that, once again, there's a problem that, this kind of text processing systems for your embedding, natural numbers are not embedded well. Okay. So the problem that happens, and that also what we'll see in if you are trying to do runtime estimations is, for runtime estimations, this tensor size values are very important. Okay.
Yeah.
For your register pressure and all these things, sometimes it may not be as okay. You may do some unrolling based on some size, but the exact size, whether it is 64 or 32, maybe just triggering something like, okay, I'm going to do an unroll by 4 or 8. Whether it is after 8, whether your tensor size in that dimension is 16 or 32 or 64 doesn't really matter. So in many cases, it is almost becoming a no-op. But if you're talking about runtime, that actual value matters, right? And then if you are not doing tokenization of those individual values, very likely your approximation will really become bad. And sometimes we have seen will be like 3x, 4x, up or down. In terms of so that is all to do with tokenization and the fact that how much of these natural numbers can be embedded well in this kind of text system, right? So this is definitely an interesting problem, which I think has not been solved well. I talked to the Granite guys, and the way they do it is they kind of bucketize, right? For example, all values less than, let's say 128 is one bucket, 128, 256 is another bucket, and then you just tokenize based on that. But that has also its own problems. So these, a good question because these are related, like the amount of tokens you can take in, especially with respect to, so if it's like, the operators and all is not a problem at all. Even the operands, even if it's high, it's not a problem. The problem lies in the actual tensor values.
Dimensions.
Yes, exactly. The shape and the dimensions is where your tokenization will play a key role. And as I said, if these are certain things which are not really dependent on your exact tensor sizes, you'll still get good approximations. But if they're dependent on your tensor sizes exactly, that's where your prediction will start becoming worse. And that's what we are seeing, that we are getting very good values with register pressure, XP utilization, those kind of stuff. But if you want to really predict actual runtimes, things related to runtimes, then we are seeing 3x off, 4x off, 5x off, and plus minus in both directions. So that has been the plan.
Yeah, that makes sense. Thanks.
Okay.
And for different tasks, right? Like estimating the register pressure or predicting runtime. For all these different tasks, do you train the model end to end, or you train the
Yes.
model once and
Yeah,
use
it's end to end, because I know you guys did let's say kind of a self-supervised knowledge graph vector representation for IR, but yeah, I mean, we wanted to keep things simple. We are just training the model end to end. I mean, getting the embedding along with the training.
Okay, thank you.
Okay, so yeah, I mean, the next steps obviously. Yeah.
One question, Dibyendu. So you get these predictions, and then based on the prediction, I mean, what is the next step for the compiler? I mean, whether you tune particular code, see if you see this kind of patterns, you unroll by 4 or don't, and you can unroll till 8.
Exactly. So those are the things. See, the ones which we are feeding into mainly is the fusion. So let's say from a higher level system, we'll get a graph with, let's say, some 30 nodes or something, and then we'll do this analysis to see, okay, if the 30 node graph itself can be fused and I am okay with the register pressure, I can tell, okay, give me the full graph and I'll do it. But if I cannot do, I'll probably suggest that, okay, I can take up to only 20 nodes and give me a 20 node subgraph rather than a 30 node one. Okay, because if I get a 30 node subgraph and I'm going to spill, I'm going to have much worse performance. And sometimes in our system, at least, if we spill too much, we can't even run the code. Okay, so these are things, yes. And later, the places where we do unrolling, we do loop interchange, blah blah blah. All of these decisions we want to take based on some of these kind of things. Like, yeah, if I do unroll by 8, my register pressure is still okay. Okay, go ahead and do it.
Sure. Yeah, thank you.
Okay. Yeah. So
I just had a small follow-up question on that. So this system is more of a user feedback thing than something that can be used by an automatic optimization system, right? Like this.
Why?
What I'm asking is, so like, no, you said in your case like loop fusion and loop unrolling. So do you, as the user, or like you as the programmer, introduce
No,
those?
the programmer is not involved in any of these things. It's all totally automatic, because once the data flow graph comes, there is only a coordinator who will interact with the ML optimization framework, right? The coordinator will give you the graph, and we can just go and do coordinate with the graph, saying that we'll either fuse the whole thing or will not fuse whole thing. We can fuse only up to so many elements, and we need to get a smaller subgraph, and that goes back, and the coordinator will probably give us a smaller subgraph, and it's all automatic. I mean, there's nothing, and there's absolute no user here involved in the entire story.
Right, and the feedback is with the coordinator. Like the feedback goes to the coordinator, and that takes care of.
Exactly. So it will just we'll just give a feedback saying that register pressure is high, we cannot handle. And then it's up to the coordinator software, which will take that and break it down and give it back to us. And there will be several iterations before we kind of accept a particular subgraph.
Got it.
Okay. Yeah.
Hi, Didi. This is Shalini here. So So for the tokens, what I can understand, like for each new dimension of the tensor, we need to introduce a different token, right?
As I said, right now the entire tensor shape is a single token because once, like what Venkat asked, we want to control the number of tokens. And
Uh-huh.
also natural numbers cannot be embedded well still, right? So right now we are kind of basing on the fact that most of these ML models use certain sizes. These are not really, the tensor sizes in ML are not really arbitrary in the sense that, it's not that once you'll see 3 cross 5 cross 7, in another case you'll see 2 cross 4 cross 6. Uh, various tensor sizes that are used. Like, for example, as I said, if you look at the transformer GPT, there are certain tensor sizes which will appear again and again and again. So basically, it makes sense to tokenize them using only one token rather than use per dimension tokenization. So we are not going to do, at least right now, we tried a bit, but it has not come out well. We are not doing per dimension tokenization.
Oh, okay. Okay, got it. So you mean like we cannot have the, but can we have some representation in which like we can, so basically in our token set, we can have independent token for the dimension, and then we can represent in some form using a single
Yeah.
token.
Absolutely. Absolutely. So you can do that. So we tried various things. We tried to take those individual things. Actually, as of now, we have not got better results. I mean, we can definitely tokenize at an individual level, right? But what happens is, as I know, you are familiar with some of these things because IR to back. So let's say I have 64 cross something, and let's say from this token, you are individually, encoding each of these values, 64 or 32 or some of those kind of things. So what happens as a result is those values that come in may not always be representative of our closeness to in the higher dimensional vector space. What we have found is the tokenization works better when we take the whole thing uh, together rather than breaking it for the tensor. It's not that I'm saying that it will not work for other cases. Like, you may figure out mechanism. Maybe we have to still figure out mechanisms where we can always break it down. We can break it down individual tokens. Individual tokens broken down, then you embed them, and then you use it in some form. It's always possible. But right now, we have not seen better results by using that. Okay, compared to representing the entire token as a single shot one token, and obviously that also helps us in keeping our the entire token set smaller compared to individual tokens. But definitely, as I said, exact natural number encoding is still kind of an open problem. If you look at it, words are fine because it's a finite set, right? Dictionary is a finite set. But natural numbers are not. So there's still some challenges in individual tokenization of natural numbers and getting good results out of it. But I'll just say that, it's still an open problem in a way. So we can, if you think of other ways. And that's also one of the reasons we are having issues with predicting runtimes. Let's say, I have a loop of 10 elements versus the loop running for 15 elements. And this kind of systems will not work well because you really cannot tokenize and have an embedding for the natural number set yet. Okay, because the natural number set is infinite. Okay. Right. So that's the problems. Moment you have a number and anything depending on the actual number is a problem. I'm not saying that tokenizing the full thing is solving the problem in any way, but as I said, because the numbers appear often together, it's working okay. But I'll say still it is an open problem. In the open problem, anything to do with your numbers in your program code, and if the thing that you are predicting is highly dependent on that number, today's whatever technology we have is not likely to do well. No matter what model you use, it doesn't matter. You can go to GPT-4 itself, it will not. And people who have been following GPT knows that GPT doesn't do a good work of arithmetic. And the reason for that is this. Why it doesn't do it doesn't do a good over arithmetic, because the vector representations or the vector embeddings of natural numbers is still a very, very approximate. It's not as good as your finite word dictionary. Okay. So that's where it is. So that's why, some of these things which are not dependent on actual runtime values and blah, blah, blah are doing much better. But moment it comes to actual runtime values, some of these will be a bit, I'll not say, I don't think it'll get such a good accuracy. Okay, so yeah, as I
So,
said,
Didi, we have one more question in chat. Does this help with optimization when the intermediate tensor shapes are dynamic?
good question. No, we haven't handled dynamic shapes yet. So as you may know, dynamic shapes, Fusion right now, we don't support for dynamic shapes. So we haven't handled that. But yeah, if you have dynamic shapes, it will be a bigger problem, because we don't know so many things about actual tensor, and it may impact things like whether we'll do unroll, whether we'll do some kind of interchange and things like that. But I'll say that it may also be doable in a reasonable manner, but we haven't investigated that. Right now, all our code runs after the high level, as I said, coordinator. After the coordinator has at least resolved the dynamic shapes to some form of static shapes. It's not that it's always resolvable, but at least the case where they do, there's a very famous shape propagation algorithm that happens in ML frameworks. So once you do shape propagation, you may be able to resolve a lot of these dynamic shapes. And so if that is done, only then after that, the user comes in and tries to do this kind of stuff. But yeah, that's a good question. I mean, right now we haven't investigated. With dynamic shapes, things will be, I think, maybe slightly more complicated. I do not know. We need to see. Okay, so yeah, as I said, next steps, we are trying to now run with larger training sets. We have at least 3x larger training set. Though I say use other models like Transformer, this slightly older slide. So we did try earlier in the year Transformers. We didn't get, too big a jump, so we kind of dropped it. Integrating in the production compiler, this is still a POC in the sense that we are trying to integrate with our Fuser system. And part of it is it's already done, and then we'll see how it all goes. And I know, as Venkat and others are pointing out, that should you do a pre-training for the MLR sequence and get the vector representation rather than doing an end-to-end stuff like kind of a self-supervised. Maybe we'll see later once we have better handle on things. And then, and we started this last part of the work. We already started that not just the high-level MLR model, but maybe even in dialects like affine or linalg or SCF, which is lower than this kind of a high-level MLR. And then we have loops. We have some kind of at least basic control flow and things like that. Whether we can do similar stuff. One big challenge will be the number of tokens will increase a big way, and then it probably go 10x higher, and then we should be able to handle 10K, 20K kind of text sequences and able to do this kind of prediction. So yeah, there are challenges of that form also. Okay, so that's where it is. And if you have any more questions, last few questions, maybe I'll take a couple of questions and then maybe we can wind up. These are the set of references. I was referring several times to this paper number 4 called Ithamal. Once again, I have not put for the granite one. There's also a new work by Huawei guys. I think it was late last year or early this year. Huawei Canada guys. They are doing some estimation on performance for while they are doing inlining using the LLVM-IR. So that may be good to have a look at but they're not exactly doing exact numbers. So the thing is, they're trying to do kind of whether X will be greater than Y kind of prediction, which probably I think is still easier to do than trying to figure out exactly what your running time for X is. Okay, so as they also would have found out that doing that may not be easy. Okay, so any last minute couple of questions? Okay, then once again, thanks guys for giving me a chance to present, and hope you have got something out of this talk, and thanks for attending, and hope to meet you in some session in the future.
Yeah, so thank you so much